All right, so I am here to speak about the mathematical complement of David Rittenhouse. The first time I started coming to the APS to study Rittenhouse, it was to figure out, really, was he a mathematician or not? And because somebody had asked me that. Who is David Rittenhouse? For those of you who don't know, he was the president of the American Philosophical Society between Franklin and Jefferson, and the only one who didn't own slaves. But more importantly, and more powerfully for him, he was the librarian of the APS. Not formally librarian, for those librarians in the crowd, but he was charged with taking care of the collection from 1773 to 1790, though they never actually said he was no longer the librarian after that point, so I have a feeling he held onto the books for a little bit longer than that. He's well known as an astronomer and a scientist, but the question is, really, a mathematician? So his claim to fame scientifically was that his work on the transit of Venus basically put the APS on the map as a scientific organization. What was the transit of Venus? It was a huge trigonometry experiment organized from London worldwide. They sent out people to view Venus transiting across the disk of the sun and took measurements from all sides of the planet. That was the plan. Maskelyne consulted with Franklin there in London about who could do that in North America, and Franklin was like, yeah, pretty much nobody south of Harvard. And so there, even though Franklin's coming from Philadelphia, I think I have a feeling there are some people in Philadelphia who wanted to kind of upend that feeling, and they pushed a group to actually do an observation of the transit. And a lot of its success depended on Rittenhouse. He built the instruments, he planned who would watch when. He did a great job, except for fainting right at the moment that the planet started to cross in front of the limb of the sun, which is just another kind of endearing thing about him. But anyway, he woke up for its exit off the limb and was able to help record observations at that point. But his mathematical underpinnings of the observations are what made the Philadelphia contribution to that worldwide experiment so notable. It's one of the few sets of observations that was given the nod in the years following 1769. Rittenhouse surrounded himself with the resources of Philadelphia. He started being a member of the library company pretty much when he moved to Philadelphia in 1770, and he probably kept all the good books of the APS collection in his own house, certainly during the war, probably, and probably after. Yes. He also borrowed books and journals, Journal de Physique, from Jefferson by stagecoach. It always made me wonder, what about all those Franklin books just down the street? But that's another issue to explore. If you look at his writings, well, there's not much left. There are scraps of paper, and there are mathematical calculations covering every scrap of paper, like this little scrap with a letter from Thomas Jefferson on there, which is just hilarious to me as a parent. This is September 6th, 1793. And for those of you who knew what was going on in Philadelphia in September of 1793, a plague, right, the yellow fever, and people are leaving right, left, and center, but Jefferson is stuck working in town. He's got one daughter and a friend 3 miles outside of town wanting to be amused. So this is him writing to Rittenhouse saying, if you're not taking your camera obscura with you when you bucket out of here, could you let the girls have it to amuse themselves? And I can just imagine one of his headaches were probably coming on as he was writing this. So there are scraps of Rittenhouse's writing to look at, and some of them are more than just scraps. Here is in his diary of meteorological and astronomical observations, which looks like it was doubling as a receipt book, a sketchbook, maybe even a checkbook. Note the cutout pages, because of course he was treasurer, I think, at this point. And there are all kinds of things going on, so all sorts of calculations. I've looked at a lot of these. But one interesting looks like a rough draft of a letter that he carefully crafts to General Schuyler for Thomas Jefferson, talking about how they are going to measure distance, the meter, using time, using the period of a pendulum. And so this is a bit of a rough draft from that. And in this little rough draft, he mentions reading an article by Euler, which is a big name in mathematics, in the Mémoire de l'Académie des Sciences à Berlin. And that set of volumes is going to come to play again. So that was a nice find there. There's the letter to General Schuyler, and in there he talks about Laplace's work. So he's very well read, Rittenhouse. Mentions Laplace's work on the lengths of the seconds pendulum, this idea of determining the uniform length for the meter by the length of a pendulum that would beat out 1 second. Rittenhouse, Jefferson loved this idea. Rittenhouse had big problems with this on the technical end, like how would you measure that length of that pendulum? Oh, would you use a metal rod, which is what Rittenhouse and later it turned out France ended up using instead of a pendulum's length? Jefferson had objections to the length of the rod changing with temperature and pressure. So, but this conversation about how to measure the length of a second's pendulum involves some mathematics. In here is basically a differential equation, the solution of which entails finding integrals of sine squared. And so later there appears a paper by Rittenhouse. It's a very interesting paper. So this is one of 2 papers that are considered Rittenhouse's mathematical work. But this one is written in the form of a letter to Mr. Patterson, who was the professor of mathematics at the college down the road, which I think used to be the Academy, then it was the College of Philadelphia, and maybe was just becoming the University of Pennsylvania. And this letter, I don't know if you can read this at all, but there's some interesting conversational tone in here. I had discovered a very elegant theorem for determining the times of vibration of a pendulum in given arches, but included a problem, the solution of which I do not remember to have met with, though I cannot suppose that it has escaped the notice of mathematicians. And he goes on to this. And then he goes on about it a little bit. I have not been able to strictly to demonstrate any more than the first 2 cases. For those of you who remember your calculus, that integral I had on the previous screen might have been something you would have been expected to, there we go. This kind of thing you might have been expected to do just in an elementary calculus class. So there's case 2, case 1's even easier, so of course, he could do that. But he's saying basically to Patterson, the professor of mathematics, should your leisure permit you to give any attention to this subject, I shall be glad to see you furnish a demonstration for the 3rd or any subsequent case, which is, of course, the hard stuff, right? Now, he had listed the results, these incredible results, which, of course, John Wallis had published 100 years before. So I think my theory is that paper of Rittenhouse addressing this letter to the professor of mathematics was just a complete burn, basically suggesting, maybe pointing out that Robert Patterson perhaps did not know of Wallis's products. Here's one of them in the middle of the page, and this book had been in the library company just across the street. Since 1770, at least, it's in the 1770 catalog. And Patterson, of course, was also a member. So how could Patterson have missed it? Or how did it come to Rittenhouse's attention that Patterson didn't know it? That I'm not so sure about. There's a little background here on Rittenhouse's sense of humor. Another guy you might have heard of, Witherspoon, the one who helped establish the College of New Jersey, Princeton, had written an editorial disparaging Newtonian mechanics and their argument. And so Rittenhouse wrote back very pithily saying, "You've just forgotten the principle of torque." And that was, cutting synopsis of what Witherspoon might have had to say. So that letter to Patterson really strikes me as just pure sarcasm. So not really a math paper by Rittenhouse. So that's one down. What about the other one? Well, here's Patterson. I thought I should give him a little bit of screen time. One thing about Patterson is in the minutes it's recorded that he objected to the collection of the books in the library going without a nameplate. And so the next meeting they said, right, you get up those nameplates and you see to it. You take care of that. In the 1793 publication of the transactions, a lot of which you guys saw volume 2 the other day, yes? In the reading room, everybody here went on that tour. Volume 2 was sitting there. Well, Volume 3 was published during the time when Rittenhouse was president. And so he's at the top of the masthead. And this chap here, Robert Patterson, is last in a non-alphabetical list of secretaries at the bottom. And it was in that particular Volume 3 that the letter to Mr. Patterson was written. Meanwhile, things were kind of going apace, or had been going apace in the London Society. They had a bit of a brouhaha in 1785, where they kicked out one of their secretaries for being too mathy, essentially, and promoting too many math papers. Gould, who was the president, wanted to have a lot less of that, so they basically ousted this chap, Charles Hutton. And so Charles Hutton, publicized his story far and wide, as well as he had written a book which landed in Rittenhouse's hands here in Philadelphia. And in that was not only a bunch of logarithmic tables, but a history of how the mathematics involved in calculating them accurately. All right, and so he provides a dozen authors' methods. Here's a little sample of Mercator. Again, you can see the previous century showing how you could raise higher powers very, very quickly. So that's here because in 2 slides you'll see why Rittenhouse is kind of doing the same thing and assumes everybody knows this. Here's another logarithm construction method by Brooke Taylor, as in Taylor's series. And the beauty of this one, of all those methods described, is this one in just one little example, one clear example, it's completely understandable. So not writing about it so much as giving one clear example possibly was inspiring to Rittenhouse. So in 1795, he read to the society this final paper, this last math paper, the only chance we have for Rittenhouse as a mathematician. A lot of people are kind of curious, how do you read a math paper? I mean, this part's in words, but then how do you read this? So maybe we understand what was happening with the Royal Society when the mathematicians would start to read their papers, everybody cleared out. Please don't go, I promise. It won't be that bad. All right, so let me get back here. So this is called, yes, now he read it in 1795. That's in the minutes, or it was read. Read, it just says, in the minutes, in 1795. He dies the year after, and his health was always bad, so maybe somebody else read it for him. The minutes are not clear. They just mention it, and they don't include the document that was read. There was blank pages there. Maybe they thought, oh, one of the secretaries will put that in there later. And so here in beautiful English is a description about how to construct a logarithm. No, I'm not going to read that to you. But here is an example. Let's see. So we skip the English and just look at what's happening here. We have this. I don't think that's quite working, but along here are just raising numbers to higher and higher powers using a kind of Mercator technique to do it really, really quickly. So they've just taken some number and raised it to the 228th power just in that. He's done that right here in this column. And why did we need this? Why do we need to raise numbers to higher powers? Well, raising one number to another power is an exponential operation, the inverse of which is a logarithm. So there, I'm done with my teaching load for this week. Actually, I was supposed to cover logarithms today, but anyway. So it would be, unfortunately, Bob wants me to walk you guys through how to construct the logarithm, but I don't think I have enough time. But essentially what happens is that you have to hold on to these exponents. You see, barely, if you can see that, it says a to the 228th. And that number 228 and other powers generated in this process then find themselves in this little diagonal set of print here. Now, for those of you who are watching sharply, anybody notice that the Wallace I had up here a bit ago, let me go back to the Wallace. Those things, there we go, right here, down here at the bottom. You see that Wallace is just publishing here something done by his friend Bruckner, who came up with what's called a continued fraction description of this summation here and of this infinite summation here, this infinite product here. Well, this is an infinite division, if you want to call it that. And so 100 years previously, Lord Bruckner had a way of describing, this is pi, by the way, 4 over pi, so it helps you get to pi, 4 over pi in a continued fraction, and nobody could figure out how he did that. Even Wallace, not Euler, nobody's really sure how Bruckner did that back in the 17th century. But that was in the library down the street, so maybe that inspired Rittenhouse, that he had seen continued fractions before. At the time that he's reading this paper, a couple of papers started to come out in the popular press. If you like, for mathophiles, here's an example. I'm going to come back to that. Here's an example of an appendix to William Trail's algebra textbook of 1789. He's slapped on an appendix in this version that talks about continued fractions. They seem to be becoming very popular in 1789, 1790s, and into the 1790s. Lots of textbook writers are adding in a little bit about continued fractions. So one more go at trying to explain what's going on here. In all these textbooks, these algebra textbooks, elementary mathematics textbooks for people going to college, they are describing a kind of low-level first step into continued fractions, where you can take a decimal approximation to something. Like here, again, we're dealing with pi. 3.14159 is what we know is a decimal approximation to it. That can be expressed as 3 plus this fraction. And so the trick is to simply take that fraction part there and look at its inverse, 1 over that, and then now you have a fraction that looks like 100,000 divided by that number, 14159, and it goes into it 7 whole times. So you see the number of times the quotient appears there, and so 3 is the first quotient, 7 is the second one. Now we have another little fragment there, which if we come over here, they've inverted, and now we have an improper fraction doing a division again. They have 15 plus. And so you can keep on going like this. Why would you ever want to do that? Euler and others proved that if you have this string of numbers, the 3, the 7, the 15, the 1, and so forth, just that little string of numbers as a handy guide, then you can generate the most accurate rational approximation to pi of any desired size, meaning of any size denominator. And for various purposes, you might want a rational approximation to pi. For example, for clocks or for orreries, which were equivalent of planetaria at the time. To make the gears in the right ratio, you might need one wheel that has 228 notches and another one that only has 25 to make things work as beautifully in your mechanism as close to the precise irrational number as possible. So my theory is that Rittenhouse knew about continued fractions from a while back, maybe having also read some Huygens. Huygens writing in the Dutch, but Rittenhouse speaks German, having grown up here in Philadelphia area. So possibly that's where he was first exposed. I don't know exactly, but if I go back here, yes, okay. So, right, so Rittenhouse is approximating the number logarithm of 99. Now, why that? That's a different type of irrational number, what's called a transcendental. And nobody had really done a way of approximating those so quickly using continued fractions. And that's where I think if this is really Rittenhouse's work here, that he should be credited. Because, for example, Lagrange had approximated only algebraic irrationals in print in 1769, and Bruckner and Coates and Euler's and Lambert's ways of looking at continued fraction expansions of E and pi, which are also transcendental, were not approximation methods. So I believe that you could say this was quite an advance, all right? Now, problems about, though, this paper. Was the continued fraction that's presented in that paper really constructed in the way that method describes? There's a real cheap and easy way using William Trail's work it backwards from a decimal expansion type thing. And so the question is, did Rittenhouse really do that, or did he kind of like come in the back door and work it backwards? Is this paper that the paper was printed or published 3 years after Rittenhouse's death? So he didn't say, let's publish that one necessarily. The people who were operating the APS after him published it in 1799. Was that continued fraction expansion his work or his editors? Sorry, I have to get to the editors. So the question really was, I came to Philadelphia to figure out who else it was in the mathematical complement, who outside of Rittenhouse could have done anything on this level. Anybody north of Philadelphia? Turns out no. And turns out that it took a few years before somebody came to our shores who was a mathematician more on that level. F.R. Hassler emigrated to the US in 1804. His uncle had actually worked with Euler in St. Petersburg, and so he had old volumes of the Novi Commentari. So when he was penniless, he sold a volume to the APS in 1804. And by 1807, Jefferson realizes that he's the mathematician we've got on the ground and appoints him as professor of mathematics at West Point. Later, he was asked to direct the Coast Survey. So a lot of mathematics and astronomy goes into any kind of surveying. In 1842, Hassler, this was published, Hassler writing in 1842 his recollections of what had happened with his mathematical work. And so I just need to point this out. Let's see. When the Coast Survey broke up in 1818, I gave in 1820 to the Philosophical Society of Philadelphia the description of the instruments and so on. Old Doc Patterson. then its president, the gentleman most acquainted with the work and its various first plans, proposed it as a great national work, and upon report of a committee, ordered it to be printed. But the Philosophical Society, being short of funds, don't let that happen, the execution of the printing was delayed so long that in 1822, the Philosophical Society of New York, where I then was, wanted it and asked for the manuscript. All of a sudden, without the slightest notice given to me from Philadelphia, the volume of the Philosophical Society's transactions containing those papers appeared in 1825. All of a sudden. With the sense in science so terribly distorted that I complained of it and asked for my original manuscript, which I had requested to be preserved, and then found that Professor Patterson, now director of the Mint in Philadelphia, and Mr. Nolte, a good theoretical mathematician, both members of the Philosophical Society who had never been in or seen or studied any particular part of mathematics bearing upon a work of that nature, had undertaken to correct, as they called it, the language of my papers. Now, it is well known that it is possible for a man knowing nothing of a subject to write upon it with propriety of expression. Thence, the most absurd errors crept into the printing. I was obliged in self-defense to print immediately corrections which rendered the mistakes less absurd, though they do not bring the expressions back to my original manuscript. And so there's the mystery, is that what also happened to Rittenhouse's second paper? How much of it really was Rittenhouse? How much of it was Team Nolte and Patterson trying to remember what he said and put it together? So that part is unclear, and hopefully I'll get some evidence about that in the future. Thank you. Is there time for questions? Or?
It's fine. Thank you. We're left with a number of mysteries. I think we have time probably for one question. Yes, here. Oh, sorry.
Okay.
Particularly fascinated that you're at a community college.
Yes.
And
well, it's my husband's fault, really.
Okay.
Yes. You see, I have a couple of Davids at home. One of them is David Alexander, who I believe knows you. He studies astrophysics. And yeah, he's at Rice. But that's why we're there. And that's why I'm at Houston Community College.
Right. Well, my question is, community colleges represent a wealth of opportunity for STEM education and for getting more kids who haven't been exposed to math and science interested in becoming scientists and engineers. So do you use this approach in your classroom? Is this kind of story fascinating to your students and engages them in mathematics? We're always looking for new approaches to get the kids really interested in exploring mathematics, but sometimes the stories and the historical basis of mathematics, how it developed, is just one way. So,
if I had more time, I definitely would. With every topic, I wish I could do a history segment. And there are organizations in the Mathematical Association of America who work diligently at providing like to-go packs of history that you can pop into your math lectures. But at a community college run by the state, we are given a huge list of topics that if we don't teach them in time, our kids take a general exam and can fail it. So we're really, really pressed for time. We teach 5 classes a semester minimum, and we're run ragged. The only reason I'm here is that a poet who was working as the math department secretary at Houston Community College tapped me on the shoulder and told me to get my nose off the grindstone and instead to apply for a Franklin grant, which he had heard of at the APS. So most of us don't have time to do research, and most of us don't have the time to include the history, though I can see that a lot of people, their eyes light up whenever I slip it in, whenever we possibly can. So I hope that we can make that possible more often.
So Franklin, I think, so I'm David Spergel, new member.
Another David.
Another David, and another astronomer. So Franklin was someone of note in Europe. European scientists knew who he was. Did mathematicians in Europe know who Rittenhouse was, and did they know any American mathematician at the time? And who was the first one that would have come to the attention of someone in Paris or Berlin?
Okay. Paris, Berlin, London, nobody thought anybody in America, and then the United States, really could do much, right? But Rittenhouse's backing of the Transitive Survey report did bring some notoriety to the American Philosophical Society and him himself. A lot of books and journals came flowing into Philadelphia dedicated to David Rittenhouse. He was also a very patriotic proponent of liberty, and there was a lot of sympathy towards the new country, towards the revolutionaries in Philadelphia, and so a lot of outpouring of affection for Rittenhouse from astronomers who really were, the scientists, mathematicians for a large part in that era in the 18th century. So if anybody knew anything about mathematics and astronomy in the United States, they knew of Rittenhouse. But apart from him, that's the problem. There's not a lot there.